Okay, and a good morning to everyone. And that was Santana. And what was the title on that one, Jonathan? Okay, we won't come back. That will probably go to Maria at the end. Okay, and in terms of, that has some lyrics that I'm not real happy with, so that's one you're not supposed to play. So just for your information, okay, in the future. Now, relative to the test coming up. Give you an idea of what I've done on the computerized base so you're aware of it. There's a practice test, chapters 1 and 2, 30 problems, 90 minutes timed. You get 90 minutes for it, you can't repeat it, and that becomes part of your homework grade.
And you can't skip it and go on and do the other ones?
No, you have to finish it once you start.
You can't skip a question and go back to it?
Oh, I think you can skip a question as long as you still have time. No, you can go ahead and jump around, but in terms of the time frame, it'll supposedly, I requested that it tell you how much time you had left. So it keeps you in mind of how many minutes. I made it 90. There are 30 questions at 3 minutes apiece on the average. And what I did, Robert, what I did was go through and look at the problems in the text. And I took 2 or 3 from each section. I only took one problem from last night's, because I didn't want more than 30, and I felt that was very recent. So the idea is don't try this until you've had a chance to go ahead and be prepared. Last thing you want to do before the test starts. Robert, your question now.
I started that practice test when we were in the lab just now, but I had to get here, so
That was the practice test in 1 and 2? No, it's chapters 1 and 2. It's not a practice test that's done by my math lab. It's my choice. I don't know what will happen there in terms of whether you can go back in and still have more time or not. I don't know how that works, so we'll have to check. Bomaro. It should be right where you have the other homework you're doing. It's listed on that same part. So I just added it at about 1:30 yesterday. So if you were there today looking at 2.6, you should have seen that right below 2.6. Or no, below 3. Okay, I've got to stop and think. 3.2, 3.3. It should be there on your page.
I think it's at the top. It says practice exam, I believe.
I'll have to check. At the moment, I don't have a quick answer for you. Let me see if I can do something here that maybe will show you what we need. Get there in a moment. Yeah, that's what I was going to try to do. Okay, just a moment. That's not going to work the way I want. So rather than show you what I have there, let me just take a moment to do this, and I'll show you where it's listed, at least what I'm seeing. That'll take me a minute to get my account up. Well, just a minute. Let me see what I've got here. I just want to show what it looks like, because at least if it's on, then I can show you what I'm seeing and what you need to look at. That'll take a moment to go. Today we're going to cover 2 sections, 3.1 and 3.2. They're very brief. They're more language than anything else. Very straightforward. So just for your information, 3.1 and 3.2. And then I don't know to what extent I want to make any effort, particularly in terms of review. From the standpoint, there's not much that we can review. I think I do want to spend some time trying to answer questions that you may have tomorrow prior to the test, but I won't go through a formal review. So if you have questions that you've been working on or you have some problem with them, then I'll try to answer those questions. So you need to have some questions from chapters 1 and 2 up through 2.6. And before we go to that, how are things going on 2.6 with the word problems? I heard one request for the R in C problem. Is there anything else that we needed to look at? Did you do okay on the voltage and the distance? Yes.
I'm confused on what the formula would be for this one right here.
When you say this
Okay.
one here, which problem is it?
It's negative 147 volts.
Okay, well, just a minute. If it's volts, you had three formulas that you had to worry about last night. One of them was distance equals rate multiplied by time. The other one was voltage, or volts, equals current times resistance. That's V equals IR. And then the other was that your net is your revenue minus your cost. So if I go to the board here for a moment, we have three formulas that we need to remember from this section. And by the way, this one is often, I should have put V, sorry. This is often, what I had in my head was that it's often done with capital letters. And instead of the V, sometimes done with E. But it's big I, big R, but it's done with the little I, little r. Current, resistance. Then you had this one, always done with small letters. Very seldom see it with big letters. And then this one, the net, and that's equal to your revenue minus your cost. So, Natalie, if I come back to this one, and they gave you some values, what values did you have? Well, you started to give me some values for I or R.
Okay, on this one they wanted you to find the current.
So I want to find I.
Yes. Okay, so it's a negative 147 volts.
So this is negative 147.
Yes.
And the R, resistance.
7 ohms.
There's your formula. There's your substitution.
That's what I just didn't know how to write it up. That's cool.
Or what is done in the text is to take negative 147 is equal to I times a 7. And that's very awkward to put I times 7. We usually say 7 times I. But then you would simply divide both sides by 7. And you would get I on the right side, although it's typical to put it in the left side. But you get a negative 21, correct?
Correct.
It would be more typical to just write it this way. And if, okay, go ahead.
You want the top where it says I equals
B over R, that's up to you. This is the way I tried to present solving the formula for one letter. So I'll come back and try to show that to you.
Okay, because I just don't want to write the wrong formula. Like I got
This is your formula.
Okay.
This is a modification of it. And if you wanted to go from here directly down to here, that's what the text is expecting.
Because I wasn't comfortable writing the V equals IR because to me it was multiplication and I didn't multiply, I divided. That's why I didn't want
Okay,
to do it wrong.
but the idea is that you substitute into the formula for the variables you have, and then you solve for the one variable that's still left. And these are letters of the alphabet to represent what you're doing. Now, R makes sense for resistance. I, for current, doesn't make a lot of sense. And one of the things I don't like about using little I in algebra is going to be the square root of -1, as we said. So this is not typical. And you'll find, I think, if you go back and look at books in circuit theory and things like that, you're going to find a big R for resistance, a big I for current, and for some reason, going back in my memory from being an engineering student, big E for voltage. But I wouldn't want to put too much money on that. Maybe a breakfast at Denny's that was free this morning,
I know, I'm almost
if they didn't run out of the food. Okay, but does that answer for you?
Yes, thank you.
Okay, I'm going to come back center. And what I wanted to show here, and I'm going to bring this down now, the way it's on my screen. Let me bring this over a little bit now. Okay, as we go to the document cam. So here's where you were looking at 2.6, and that's where I had the date on that was 12/3 today at 11 a.m. This I had not opened up until today at 11 after class, but down here it says practice test for chapters 1 and 2. It's a time test, and I had it open yesterday at 1 in the afternoon, and it will close at 10 a.m. just prior to the test. It's 90 minutes and you can take it at any time you want before the test. Now, is this the kind of selections you see when you go to your home page?
It doesn't show the project session. It will show all the show.
Not exactly similar.
It will should show something there like this because I had it open as of available on yesterday at 1 p.m. and you aren't seeing it in that form?
You have to click the show all.
All it says is section and see your score.
Yeah, it's on an announcement, and I'm... Okay, so at this point on the announcement part, let me come back to that. Let me bring this down, and let me... Okay, that's not going to work because if I go ahead and log out, let me try this. Okay, and I'll show you what the let's come off there for a minute. I'm going to go to the announcement and show you what's reading there. But you're saying you have to show all, James, in order to get that to come up? Show all the assignments? Okay, this is what I'm seeing on the screen. Let me bring it down so you can read it. This was the announcement practice test 1. As we go to the document cam, practice test 1 is a timed test, 90 minutes, and cannot be repeated. You can take it any time before the test on Thursday. Your grade on the practice test is part of your homework grade. And then it says, see the syllabus, and that again is listed as of yesterday on your announcements. Okay, so at this point, just be aware of it, and Loretta can show you, if you have questions, how to get there. Okay. Now, back to 2.6. Are there other questions from the homework on the word problems? Loretta. Okay, coming back to here, where I have I times 7, that is a direct substitution. Now, we are going to spend time today, and this is just anticipating a little bit like 10 minutes ahead or so. If I have 7 times I, we call the I the variable. We call the 7 a coefficient. So this is going to be referred to as a coefficient. And because in mathematics I has a very special meaning, this should not have been the letter used. But let's say I had 7x, where x is generically referred to as a variable. So this part is the variable. The product of a coefficient times a variable, so I have 7 as the coefficient, x is the variable, is referred to as a term. A term of an expression. So we refer to algebraic expressions and without trying to formalize that in a very detailed way, it simply means you have a variable somewhere in an expression, and it consists of additions, subtractions, multiplications, and divisions, and you have a variable in it. We call it an algebraic expression. If you have nothing but numbers, it's called a numerical expression. This is a pretty darn simple one. When you only have one, a monomial. Remember when we talked about 1 bar over the m? 2 bars over the m would be a billion. Well, when you have 2 bars, we call it bi for 2. So this is a monomial here. But if I have 2 terms, such as 7x plus 3, there are 2 terms, so we refer to it as a binomial, just like we did a billion. If I have 3 terms, such as, let me write this now as a binomial. If I had 3 terms and instead had something like x squared plus 7x plus 3, we call that a trinomial. Like we had trillion. Works the same way. Now, if we had 4 bars, we called it a quadrillion. You don't call them quadromials. You just say polynomial, like Polynesia. Mini, poly. So a polynomial, and by the way, interestingly, a monomial, a binomial, and a trinomial are all considered polynomials. So generically, a polynomial could be 1, 2, 3, or more terms. Just a vocabulary, but an important vocabulary. This trinomial is in one variable. Now, I can give you a monomial in 2 variables. IR. That sounds crazy. It sounds like bad English. I are going instead of I am going. But I times R is a monomial with 2 variables. More typically, if I want to look at a monomial with 2 variables, I might write x times y. And that is a very typical expression in algebra. 2 variables, 1 term. So it's a 2-variable monomial. You need to speak the jargon. Okay, and it's just learning the language. Now, there's some unseens here. There's an unseen coefficient, correct? If you don't see a variable with a coefficient, it's there anyway. It's the 1. If you see a variable without an exponent, it's there anyway. It's a 1. So that's really 1 times x to the first, y to the first. 1 term, 2 variables, coefficient of 1. Michael?
And that's the identity property?
No, the identity property says if you multiply 1 times anything, you get what you had. So by the identity property, I know 1 times xy is xy. But the 1 as a coefficient is independent of the identity property. Now, 1 is the identity for multiplication. I'm sort of skirting around it a little bit, so you just have to be careful how you're saying it. A comment that I'm not real comfortable with in the text has to do with this 3. Thank you, Jonathan. That 3 up there. The 3 is a term. It is a constant. The number by itself is referred to as a constant as opposed to a variable. Now, your text comments that the 3 is a coefficient. I'm not comfortable with that. Coefficients are in front of variables. Now, if you wish, remind you of days past with basis, a 3 is the same as 3 times x to the 0. So technically, the 3 is in front of a variable. You just don't see it because it's x to the 0. So they bring this up from the standpoint in the computer when you enter a coefficient for this constant term, they will expect you to say the coefficient is 3. Technically, it's a constant, and you will not find in an algebra class typically considering that 3 a coefficient. The coefficient is in front of a variable and is understood to be multiplied times the variable. Now, while we're at it, since I'm on this rip about vocabulary, here goes. The exponent on that x is 2. We say that that term has degree 2. Second degree term. The exponent on this second term has a 1. It wasn't written there, but it was understood. That's called a first degree term. So a second degree term, first degree term, technically a 0 degree term because the exponent is 0 on the variable if you wrote it. One more time. This is a trinomial, 1 variable, second degree. Because the degree of the trinomial is your highest degree term. One more time. Degree 2, first term. Degree 1, second term. Degree 0, third term. What was your highest degree? 2. Therefore, second degree trinomial, one variable. That's the way you have to identify it. So this binomial I have down here, 7x plus 3, look at the monitor if I'm in your way. 7x plus 3, what's the understood exponent on the x? 1, the unseen 1. So what's the degree of that term? 1, first degree. Second term, degree 0. How many terms? 2. 2 terms. Binomial. First degree, binomial, one variable. Single term, monomial, two variables. Degree, 2. Add the exponents if the variables are multiplied together. So if I have an x times a y, x to the first, y to the first, add the exponents on the variables to get the degree. First, the coefficient, 1 exponent. So you'd say monomial, second degree, 2 variables. Okay? Okay. Again, one term, monomial. How many variables? 2 variables. What are the sum of the exponents on those 2 variables? 2. 1 and 1 is 2. Therefore, second degree monomial in 2 variables, x and y. Jonathan, I need camera 1 here, camera 2 free in that side, please, so I can travel. There was another question or not? Good. Okay, catalog time. So we go to the board. This is considered a general trinomial. Okay, we're waiting for something to happen. There we go. General trinomial, second degree, one variable. Notice something very important. The coefficients are the first part of the alphabet. A's, B's, C's, D's, E's, and F's. The variable, typically second part of the alphabet. Okay? Second degree term, first degree term, 0 degree term. The coefficient A, coefficient B, constant C. Question, Michael? The only letter you see is an X. You don't see an X and a Y. So let me do the more general 2 variable general second degree, which would be A x squared plus B xy plus C y squared. Second degree, 2 variables. Okay. Question? Does it make sense? Here's that same xy you talked about. 2 variables, x and y. There's one variable, there's another variable, 2 letters. The last part of the alphabet. We typically use X, Y's, and Z's. And the reason we can limit ourselves to that, we live in a 3-dimensional world.
What about the other one?
The other dimension?
No, the other Y.
What other Y? That's the same Y this is. It's just to the second degree. Each term here, degree 2 in X. Degree 2 in X and Y. Degree 2 in Y. What's the highest degree term? 2. Therefore, we say second degree trinomial, 2 variables. And then, in an algebra class, just to show you how the same language works, although we tend to do this, that's the more general second degree equation in 2 variables. But notice, degree 2, degree 2, degree 2, degree 1, degree 1, degree 0. General second degree equation in 2 variables. And it is one somewhat unusual circumstance that we talk about big A, big B, big C, big D, where here we use little a, little b, little c. That's not as consistent as I would like. But this you would see in an intermediate algebra. This you would see in a beginning algebra. This is in the beginning algebra. Okay. So all we're doing now is identifying degree and coefficient, language, jargon. You got to speak the talk. That's the first part. Technically, that is 3-2. Now, in 3-1, we evaluate an expression. So, for example, I give you 3x squared and ask, what is that going to be if x is equal to 5? Evaluate this if x equals 5. So you substitute. So the 5 is squared. That's 25. 3 times 25, 75, and you've evaluated. Is there a question there? Yes?
Does it make a difference to saying you're not speaking on it? Is there ever a lowercase?
In terms of what I'm doing here, and that maybe should be a little smaller here, you don't want to switch cases. Otherwise, what's being asked, capital versus small letter. So if I have a big A, big B, big C, and so on, you don't want to suddenly rewrite it with little a, little b, little c, because there's going to be a distinction sometimes between what those letters represent. You can't, at will, go between little case and big case. Now, let me, again, so much of this, if you don't put it in context, doesn't make a bit of sense. This was 3x squared. Okay, let me look at a table we would create. Yeah, I'll do it this way. Let's just do that much. X and x squared, just to make things simple. If x is 1, what's x squared? 1, isn't it? 1 times 1. If x is 2, what is x squared? Agreed? 2 times 2. If x is 3, we get a 9. If x is a minus 3, I still get a 9. Because I'm substituting, this is minus 3 squared, which is 9. So a minus 2 will give you what? A 4, and a minus 1 will give you 1, and so happens that if you put a 0, you get a 0. Now again, we're talking about an expression, x squared. There's a difference between an expression and an equation. Now you've looked at things like this. X plus 5 equals 8. And we've said you can just look at that and tell me the solution is 3. That's an equation, correct? What we often do with an expression like x squared is set up an equation with 2 variables. Y on the left side, x squared on the right side. So this becomes x, y, and I suddenly have a set of ordered pairs, just like we did in Math 10. And you remember how we plotted those. So, again, based on what you've done in Math 10, and I'd be in deep trouble if I did this in a general Math 20. There would be total confusion at this point, typically. But now I can plot the pairs I just did. Start with the bottom one. Where is 0, 0? That's at the origin. Okay, now we had a 1 for x and a 1 for y. So that says go over 1, up 1. Down here I had a negative 1, 1. So over 1, up 1. Then I did what? Over 2, up 4. So this looks to be about here. And over negative 2 and up 4. And we get this pattern here, correct? We've got a point down here. Not a V. It looks like it might be a V, but if I bring this down here, it's missing this point. So what you get is this curve. That's called a parabola. A parabola. But it's not pronounced that way. It's a parabola. Whether it's an eraser, a rock, or a ball. If I toss it from here to the door, and you look at the path it goes, it'll be that curve. Anything you toss up in the air, throw a pass, it's going to follow a parabolic curve. A parabola. Parabolic. Reflectors in a headlight are parabolic. Okay? The reason for that was a parabola. Okay, here's my parabola on its side. Put a light here, a bulb, a filament. This is the reflector. Okay, so the old-fashioned headlamp looks like a moon, but that was mounted on a fender of a 1930 car. And the idea was then, this was the lens out here, and if the light comes out from this bulb, it hits here, here, all these come out parallel. That's a property of that parabola. And so, when you make a reflector on a headlamp, if you just want a beam of light, you put the bulb at a certain spot. Now, if you don't put it exactly where it should be, you get more of this. But you've seen these flashlights where you can turn the front of it and you can narrow the beam down or you can get it broad. All you're doing is moving this back or forth, and you either get a very nice straight beam or it floods out. And that's sound. On the sidelines at a football game, you see these reflectors that are curved. Same idea. The sound comes in, the microphone's right here, and it picks up a sound that is not heard as easily just sitting on the sidelines. So the football games, this is used. Golden Gate Bridge. Now I say that like you know what I'm talking about, and I realize that may not be the case if you haven't been to San Francisco, but if you've seen a suspension bridge, now that same arc between two posts called piers. Cables coming down supporting the roadway. Parabola. 3 different applications, and it all comes from this equation. Okay? And by the way, these all come from an ice cream cone. So the next time you go and buy an ice cream cone, and you chew the cone at a particular way, you'll get one of several curves. One of them is a circle. Another one is a parabola. Another is an oval. You've seen ovals for pictures. That's technically called an ellipse. And then finally, the hyperbola. The hyperbola, that was done badly. Let me try that a little more carefully. Two branches to a hyperbola. Those are called conic sections because they come from an ice cream cone. This one, slightly rotated, becomes Remember that product I had, xy, monomial, two variables, second degree. If you say that's equal to 1, what you actually get, and I'll draw it more carefully, this particular one looks like this. That's rotated this. Folks, that's pre-calc, that's intermediate algebra, that's calculus, that's beginning algebra, that's the language. This started out 2,000 plus years ago, looking at cones. The cone then was simply an hourglass that they measured time with. Those are two cones put together, and you get the hourglass. And they realized you could get a circle, oval, parabola, or hyperbola. Elliptical orbits, the planets. Okay? The parabola, what happens due to gravity. The circle, you're familiar with when we look at two-dimensional representations of the moon and the sun. The only one that doesn't make a lot of sense is the hyperbola. But if you get into Einstein's theory, then you have a couple things to deal with. One is hyperbolic geometry, and also to realize there's more than 3 dimensions in that theory. And so we have more than an x, y, and z. So you have to have a 4th dimension, which we've done a lot with in terms of science fiction and so on. So the language of algebra. I want you to at least know what a circle looks like. I don't think that's a problem. And you know what the Golden Gate Bridge looks like, and that's a parabola. And you know when you throw something into the air and it comes back down, it's following that same arc, called a parabolic arc. The oval, every time you buy pictures, put them in a frame, you tend to see the oval. Easy to draw, by the way. Easy to create with ovals or ellipses. And the hyperbola, not too much meaning for you right now. But it's the language. That's all we're talking about in evaluating expressions. So if I wanted to take a look, let me come all the way over here to the left now, in terms of what I have here. If I put this equal to 0, okay, this is a second degree, 2 variables. It will be one of these 4 curves. So again, set this equal to 0, or equal to 1, or equal to 5 or something. You're going to get either a circle, parabola, ellipse, or hyperbola. And we have ways of dealing with it. Come up with this one. We set this equal to 0, and you solve an equation. So let me give you a much easier one. Here's a version of this one, an example. Now that's a second degree binomial equal to 0. Can you tell me a value at x that'll make that true? 0 won't do it. 1 will, won't it? 1 squared minus 1? You've evaluated this. Let x be 1, and you get 0. So you have a solution. Okay, is there another value that will work? There is. Let's look at my table. When you had x at minus 1, what did you get? 1. So back to here. If x is minus 1 and I square it, I get 1 minus 1 is 0. There's 2 solutions, -1 and 1. So that's solving a second degree equation in 1 variable. And that's what we do in algebra. Okay? Now I'm going to leave that there for a minute. Let's look at what we've done in the book. We've covered both sections. Let me show you where we're headed. You know what a polynomial is. Look at 3.3. Document cam, please. We add, subtract, and simplify. So we know what polynomials are like. And we're going to be able to add them and subtract them. And then after we've done that, what? Multiply them and divide them. And then factor them. Well, when we get to polynomials, we will think of dividing them, but we won't really divide. What we'll do is write them as fractions and cancel. But sometimes we still talk about a long division problem with them to avoid having to be so clever with the factoring. Now, let me back up a little bit. I don't know if these objectives make things better or worse. I think it's a simplification that it's nice to see, and it's the current buzzword in teaching. Have objectives. State your objectives, and all will be good. And I'm being very cynical and sarcastic in the statement. But nonetheless, let's go to 163. Identify monomials. Can you now identify a monomial based on what we've said this morning? Could you do that? Could you identify a monomial in a group of polynomials? I hope you can. If you can, then I've met that objective. Let's come off there for a moment. Can you do this now? This is objective 2, page 164. Can you identify the coefficient and the degree of a monomial? I hope you can. You should be able to. Okay. Coming off there. I'm going to skip 3 for a moment because I still need to talk about that. Objective 4. Can you identify a polynomial and its terms? Otherwise, is it a monomial, binomial, trinomial, or polynomial? And can you identify which terms are there? So, for example, as I slide down here, every one of these expressions is a polynomial. The first one is a trinomial, one variable, degree 3. Does that make sense? Trinomial, 3 terms. Degree of this term is 3 because its exponent is 3. Degree of the second term, 1 because the exponent is there even if you don't see it. It's a 1. This is your constant. 3 terms, trinomial, 1 variable, degree 3. What's this one? Binomial, 2 terms, 1 variable, degree 1. Okay, this is going to be called, we don't say quadromials, we'll just say a polynomial. 3rd degree, 1 variable. Next one, trinomial, degree 2nd, 2 variables. If you can do that, we've got those objectives. Okay. 2 things yet I still need to cover, but let's go to the 5th. Can you identify the degree of a polynomial? We just did, so you should be okay in that objective. The example at the bottom of the page. There is an expression, and the degree is 6 because why? The highest degree term was 6. Degree 3, degree 6, degree 2, degree 1, degree 0, highest degree 6. That's the degree of your polynomial. Okay, enough on that? Question, yes? Yes, the polynomial degree is the same as the degree of the highest degree term. Okay, this one is one that I need to talk about. How we write polynomials. This is objective 6. Descending order of degree. Now that may not make a lot of sense to you, but let's come to the sideboard. Standard writing. Now, all we're doing is trying to make sure that when you write something, you don't look foolish. Otherwise, you want to build confidence. So this is degree 2. This is degree 1. This is degree 0 because I could do that. Notice they stair-step down. 2, 1, 0. That's very typical. Here, notice that I've got two variables, and so this is a little more awkward to see it. But if I gave you, let's come back to an example. Let me see. Let's slide down here a ways. Just moving back. If I gave you this, 6x to the first minus 2x squared plus 5x cubed minus 1, that would not be in standard form, because the exponents aren't stepping down in descending order like stair steps. So you'd rewrite this as 5x to the third minus the 2x to the second plus the 6x to the first minus 1. Now it's in descending order.
So you want us to rewrite like
That is the general form when you write a polynomial. You don't worry about the subtraction and addition signs. You just carry them with the term and rearrange. There's another idea that's rather important here called like terms. And it's not that terms like each other, like people do. But if I wrote 3x minus 5 plus 2x, you would say these two terms have the same variable, same exponent. They are like terms. So we combine them and say you have 5 of them now. And by the way, if you wanted to write this as a product, you'd now use the distributive property and do that. We combine like terms. They are terms with exactly the same variable at exactly the same exponent. So if I have 3x squared plus 5x minus 2, there is nothing I can do. That exponent is an understood 1. This is a 2. These are not like terms. Michael?
When you say combine, you mean add them?
Yeah, combine them, meaning add them or subtract them. If it had been a negative 2x, then I would have just had x. Okay? Let's leave that. So if I look at a problem where I'm supposed to combine like terms, and there was a statement for that where I'd like to go back and page 165, look at identify like terms. Okay, so it says like terms, monomials that have the same variable raised to the same exponent. So x squared and x squared, like terms. X squared, x cubed, not like terms. And you just have a whole bunch of problems in which you're trying to make sure that you can identify the degree, how many terms, combine like terms. And is there anything else that I want here? Yes. A definition. This is a phrase that really, at times, creates havoc. Sometimes it's said, simplify, or simplest form. Basically what this author is saying, written with the fewest symbols possible. So written with the fewest symbols possible. So you combine like terms. Okay, coming off there. There's a word in mathematics that's often used relative to this. It's called paucity. Okay, it's a word that you can use in your English class. Paucity. P-A-U, city. Okay, P-A-U-C-I-T-Y, paucity. And it means pretty much what we said here. Writing the fewest number of symbols possible. So that means you combine like terms when you can, so you have it in simplest form. So if I had, that we, over in the sideboard a moment ago, we cut to there, Jonathan, where you have the 3x minus 5 plus 2x, that was not in simplest form. When I wrote it as 5x minus 5, it was in simplest form. When I factored it into 5 times x minus 1, that was useful because, let's just take the next step here. If I had an equation with that expression on the left side, sorry, that was a minus 5. I would use the distributive property to do this, and then it's pretty darn obvious that x equals 1 makes that 0. And now I've solved an equation. So we simplify from here to here, and if it's an equation, I can use the distributive property to rewrite it so I can see a solution very quickly. And we'll be doing that a little bit more. Okay. I think I've covered the objectives there. There are 74 problems in this set, and I gave a bunch of them. Now let's go back to 3.1. That was where the heavy vocabulary was in 3.2. 3.1, you were supposed to be able, as an objective, to tell the difference between an expression and an equation. Let's look at that. Page 159. The difference, sorry, let's come off there for a minute. With a soft cover book, I can't hold the cover so it stays straight. Let's try it again. The difference between an equation and an expression. What do you need for an equation? The equal sign. That's simple. If you don't have an equal sign, not an equation. It's an expression coming off there. Then, what we did already, but just bringing this again to your focus, to evaluate an expression. You substitute. And then follow order of operations. So here's an example. X squared plus 5xy, leave it there for a minute, 5xy minus 7, x is minus 3, y is 2. So you can see the expression. So what would you do? You put a minus 3 where the x is. That would be 9. You now have 5 times this product. The product is negative 6. That would be a minus 30. Then minus a 7. And you can see exactly what we have there in the solution. That's evaluating. And that's the way you should do it with parentheses. Okay, coming off there. There's only about 2 more examples, and then the excitement's over in this section. There's not much here to get excited about. Okay, there's an expression. Now, the only thing that makes this exciting is because it's got a radical in it. Note the radical stops right where my pen is. Now, I had a professor who liked to put a little notch here at the end to say the radical's over. This is bad notation. It would be much better to have 5m in plus 7 times this. Then there's no question about what's in the radical or not in the radical. So let me come to the sideboard on that. We get real sloppy when we do things at times longhand. So if I do this, and then over here have plus 5m, if you aren't clear as we go to the board, not that board, this board, if you are not clear, then you don't know whether this becomes part of this or not. If it is, you combine. So I sometimes drop there. To get around that, it's much better form to say 5m plus 7 times the square root of m plus n. Now it's not ambiguous. So this would be better form than this. And a lot of what we're doing is knowing what form to use so you don't get confused. If I evaluated that with m and n at particular values, I just substitute. So for example, if I take m is 2, I don't like that. I'll take 12. And n is 4. Then I would say 5 times 12, notice I put it in parentheses, plus 7 times the square root of 12 plus 4. Then you do what? Radical first. Add them together. That's 16. So that's going to give you a 7 times a 4. We have a 5 times 12 is 60. So I have a 60 plus 28, and I have 88 when I'm done. evaluating an expression. And that should be fairly straightforward for you. Leave that there, because I'm running out of time. The only thing that's left, just a caution here. One we've talked about before in Math 10, and I'll just quickly to the document cam. Document cam, please. Don't divide by 0 in the story. We can say 0 over n, that's 0. 0 over 0 is verboten. Don't do it. Okay, so with that said, there's a bunch of problems in this set. I think they go from 1 to about 50-something, up around 60. There are about 180 problems or something. There's an assignment, do both of them by tomorrow, 3.1 and 3.2. I'll get 3.2 set up so you can do that. And so, Jonathan, we've been listening to Santana.